Malaria is an infectious disease caused by a series of protozoan species of the genus Plasmodium. There are 5 different malaria species that all cause the disease in similar ways and infect the host through transmission by the female Anopheles mosquito. Infection causes a variety of symptoms, including cycles of elevated temperatures, chills, sweating, muscle aches, fatigue, jaundice, and anemia. The Plasmodium species has a 2-stage life cycle, with reproductive phases in both the mosquito and the infected human host. It is extensively complicated, so do not be alarmed if you don't understand it first time round. When the mosquito draws blood from an infected host, the gametes of the Plasmodium, called gametocytes, are taken up in the blood, and male and female gametocytes fuse to form zygotes inside the mosquito. These zygotes then mature into sporozoites before migrating to the mosquito's salivary glands. The mosquito is now loaded with the deadly malarial parasite, waiting to infect an unsuspecting human on its next bite. The human reproductive phase is more complex, so turn your study music off and grab a cold bottle of water, because this is going to be intense. When the mosquito bites a host, it injects these infectious sporozoites into the bloodstream, where they travel to the liver. Once the sporozoites have invaded the liver cells, they will reproduce rapidly and differentiate into merozoites. These merozoites will then exit the liver into the bloodstream, where they invade and consume the contents of red blood cells, causing fever-like symptoms in the host. The red blood cells then rupture, releasing the merozoites to infect more red blood cells. A small portion of the protozoa in the liver will not differentiate into merozoites, but into gametocytes, which will then be taken up by the mosquito to continue the Plasmodium life cycle. The World Health Organization recommends the treatment of malaria with artemisinin-based combination therapy. However, artemisinin resistance has now been confirmed in 5 countries, causing a worldwide race throughout the scientific community for a new antimalarial drug. The drug we have synthesized is 3,4-phenol-5-1-R-5-S-6-6-dimethylbichlor. Naming complicated molecules like ours in organic chemistry is not a simple exercise, as the name must uniquely describe the position of every atom in the molecule. Instead, we can describe general groups of drugs based on their core structure and their associated properties. Our drug has a triazolopyrazine core, which targets the sodium ion pump PFATP4, which is responsible for maintaining a low internal sodium concentration, a necessity for normal enzyme functioning. A low cytosolic sodium ion concentration also creates a high concentration gradient which the protozoan uses as a source of energy. We hope that our drug would successfully disrupt this ion pump, killing the parasite and acting as a new treatment for malarial infections.